In our previous video, we started from our continuous formulation. We stated that we were approximating C hat by the sum over all of the nodes in the element C sub j times n sub j. Furthermore, we stated that we were using the Galerkin approximation so that our weight functions w sub I would be the same as our basis functions n sub j. When we substituted that into our continuous formulation, we arrived at the spatially discretized formulation that's shown here. Note that we still need to consider our temporal term, the partial of C sub j with respect to time. Let's turn our attention now to that term. We know from the analysis that we did for the 1D problem and from calculus that we can approximate the partial of C with respect to t as C evaluated at t plus delta t minus C evaluated at t over delta t. In fact, we know from the calculus that in the limit as t goes to 0, we will recover the partial of C with respect to t. So the continuous approximation translates to a discrete approximation, C sub j, n sub j, evaluated at n plus 1, minus C sub j, n sub j, evaluated at step n, all over the change in time. And we know that the n sub j's are not functions of time, so we also know that we can take those outside of the parentheses. So we have a way of evaluating C for the temporal term. We can evaluate C at n and n plus 1, and we can find the difference to determine how C changes over time. But when we do that, where do we evaluate the spatial terms? Do we evaluate them at step n, or do we evaluate them at step n plus 1? Just as we did with the one-dimensional analysis, we're going to use the theta method, so that C of j at n plus theta is defined as theta times C of j at n plus 1 minus theta C of j at n. And when we do this, we see that if theta is equal to 1, then all of the terms will be evaluated at step n plus 1. This gives us a fully implicit method. At the other limit, if theta is 0, all of the spatial terms will be evaluated at C sub j at step n, giving us a fully explicit method. We can do it somewhere in between, and we know in fact that for theta equals 0.5, we recover the Crank-Nicolson scheme. Let's substitute these approximations for C sub j into our spatially discretized formulation. When we do that, we obtain a left-hand side term that includes first the temporal term, then theta delta t times the conduction or diffusive term, plus theta delta t times the convective term. And all of these are the coefficients for Cj at the new time step n plus 1. The right-hand side contains the temporal term, 1 minus theta delta t times the dissipation term, 1 minus theta delta t times the convection term as coefficients to Cj at time step n. In addition, for this problem, our source is not a function of time, and our boundary flux condition is not a function of time. So we will evaluate them in their entirety, and we'll add them to the right-hand side because they're known. So all of the terms on the right-hand side are known. This provides us with the complete discrete formulation for our application. Our next step is to choose elements and basis functions and then build out a solution.